Since the first Earth Day 50 years ago, researchers have made tremendous strides in understanding our complex planet. Working together, engineers and scientists have harnessed technology to make first ever measurements of the Earth and our environment, taking advantage of instrumented satellites and the unique vantage point of space. Today, we are observing the Earth in more detail and looking at more processes and variables than ever before in human history. Our scientific satellites are taking the pulse of the planet everywhere and all of the time. Scientists and policymakers are using the satellite measurements to learn about how our Earth works, how the many processes on land, in the atmosphere, and in the ocean interact with each other to create our present environment, how those interactions will change as the climate evolves, and how we as humans can alter what we are doing today in order to safeguard our planet for future generations. Thanks to satellites and to science, we now know much more about the Earth than we did on the first Earth Day 50 years ago, when I was just 15 years old. Let me give you some examples of questions that we can answer today, but that we couldn't answer then. On the first Earth Day, we didn't know quantitatively whether and how global sea level was changing. We only had records from scattered coastal tide gauges. Today, from more than 27 years of data obtained by exquisitely precise satellite instruments flown by NASA and our international partners, we know with precision and accuracy that global sea level is relentlessly rising. The satellite instruments that we use to measure global sea level are so sensitive that if we were to put them in an airplane flying at 40,000 feet, they would be able to detect the bump caused by a dime coin lying on the ground. From these decades of continuous satellite observations, we know that the global average sea level is rising 3.4 millimeters per year, and the rate seems to be increasing. Even more importantly, from those satellite measurements of sea level and separate satellite observations of gravity changes, which are related to changes in the amount of water in the oceans, we know which processes are causing sea level rise. Nearly 2/3 of the observed rise results from adding water to the ocean by melting ice sheets and glaciers on land as surface temperatures around the globe increase. The satellite data tell us, though, that more than 1/3 of sea level rise is the result of heating the upper portions of the ocean, which causes the water to expand, just like the fluid in an old-fashioned thermometer expands when temperatures increase. So, thanks to decades of precise global satellite observations, we know that the changing climate is resulting in global sea level rise, and we know how much of the rise is the result of putting more water into the ocean, and how much of the rise is the result of heating the upper ocean. With so much of humanity worldwide living in coastal areas, and with so much of our nation's economic and defense infrastructure located near present-day sea level, the climate-induced rising ocean will have a significant impact on civilization and on our nation. On that first Earth Day, scientists knew that long-lasting greenhouse gases in the atmosphere influence our planet's overall radiation balance, whether the Earth warms by trapping some of the sun's energy, or whether it cools by radiating out more energy than is absorbed by the sun. They knew that human burning of fossil fuels, coal, oil, and natural gas, increased the atmospheric concentration of carbon dioxide and other potent greenhouse gases, and also likely caused the planet to warm. But we didn't know how much of the human-burned greenhouse gases stayed in the atmosphere, and we didn't know the ways in which natural processes control exchanges of carbon dioxide between the atmosphere on the one hand and the land and ocean on the other hand. Indeed, at that time, some people thought that almost all of the human-caused CO2 that didn't stay in the atmosphere was taken up by vegetation on land. Thanks to satellite missions, such as the Orbiting Carbon Observatories 2 and 3 from NASA, and international partners such as Japan, we can now measure and monitor atmospheric carbon dioxide levels globally with high space and time resolution. These measurements from truly cutting-edge instruments show how our planet breathes, with land vegetation and phytoplankton in the ocean taking CO2 from the atmosphere during the sunlit growing seasons, while putting some CO2 back into the atmosphere during our dark winter seasons. Indeed, by analyzing the satellite and other measurements, Earth scientists now know that on average, only about half of the human-caused CO2 from fossil fuel burning stays in the atmosphere, while the other half is taken up almost equally by the oceans and the land vegetation. The satellite measurements are helping us understand remaining open questions, such as why some years almost all of the human-caused CO2 remains in the atmosphere, while other years almost none of it does. Our planet is complicated, but detailed, global, long-term satellite measurements are giving us insights into processes that have been mysteries for all of human history to date. On the first Earth Day, and even until the start of the 21st century, no one knew how much rain fell on our planet. Scattered rain gauges on land provided important information, but 73% of the planet is covered by water, and it is not possible to make accurate rain rate and amount measurements on oceans and large lakes. Today, however, thanks to precision measurements from joint NASA and Japanese satellites, such as the Tropical Rainfall Mapping Mission launched in 1997 and the Global Precipitation Measurement Core Observatory launched in 2014 and still operating today, as well as thanks to instruments on more than 10 other satellites that together form the Global Precipitation Constellation, NASA researchers are routinely producing global rain and snowfall maps with spatial resolutions of 6 to 12 miles and time resolution of an hour or less. This information, which can only be obtained from combining observations from many satellites all orbiting at the same time, is improving severe weather and flood warnings and weather forecasts around the world. Thanks to long-term, global, frequent, high-resolution satellite measurements of many different environmental variables, today, research and decision makers alike have available observations and understanding that could only be hoped for 50 years ago on the first Earth Day. NASA, other US agencies, and international partners across the globe are planning, building, and launching even more and more capable Earth-observing satellites. All of us have the responsibility to help advance the technological and Earth science revolutions that together have given us such insight into our complex planet, and that will improve the lives of every human during the next 50 years and beyond.